Okay, so here's video 2 of class 18, and we're going to deal with a, I don't know, it's like sort of like a hair dryer kind of thing, maybe? I don't know. It's got a jet that's shooting up this sphere that weighs 0.12 pounds, and air is blowing up, and it's suspending it due to drag, and they give us that the drag coefficient is 0.5. I want to determine the reading on this pressure gauge right here. So it's sort of a combination where you're using a little bit of Bernoulli here. So if we were to look at this, we would say, well, the weight of an F at BD right there, just to show this right here, that the drag and the weight were going to be equal to each other in order to balance this thing out right here. So drag equals weight in this case. And the drag that we would find is going to be CD, the drag coefficient was given rho and V. Let's call this point 2 right here, and we'll call this point 1. And so we'll call that 2 squared and then A. So rewriting this thing around, we could find what the velocity, we can anticipated velocity right here is going to be by taking 2 right here. So that 2 goes over there, and we're going to divide out by the drag coefficient, and I just wrote that D for some reason. I guess I'm kind of tired. It's 9:18 at night. I got so much more work to do, but I'm not complaining. So throw in some numbers in here. 2 times the drag, which is equal to the weight, 0.14. Divide by the drag coefficient, and the density, 2.38, e to the minus 3. And then we want the area, so it's going to be the profile area of this, so pi over 4, and the diameter, it's 2 inches, so that's 2 over 12 squared, and all those units should work out, so we get 103.9 feet per second. So we know that we could have the conservation of mass, right? So m dot equals m dot, and therefore, 1 equals 2, and therefore the density right here, and that just cancels out because of this. So we could say that V1A1 is going to be equal to V2A2. And they were nice enough to give us the areas there, so we can find out what the velocity of 1 is going to be by taking V2 and multiplying it by A2 over A1. So we have 103.9, and the area at 2, see if I have that right, yep, is 0.3 up here. And the area 1 is 0.6, so we could probably do that math, 51.93 feet per second. So let's take a look at our good friend Bernoulli between these 2 points, P1 plus 1/2 rho V1 squared plus gamma Z1 is equal to P2 plus 1/2 rho V2 squared plus gamma Z2. And there's really no elevation change, or any elevation change is going to be negligible because we don't have a very large gamma going on here. It's because it's air. We can also say that P2 is going to be atmospheric. So we can find P1 is going to be equal to 1/2 rho, and we could say is V2 squared minus V1 squared, or 1/2 2.38 e minus 3, and then take 103.9 squared minus 51.93 squared. So we end up with the pressure that we're predicting is going to be at this gauge in order to accomplish this miraculous feat. It's going to be 9.626 pounds per square foot, which if we divide by 144, we get 0.688 psi Let's call it G because it's gauge pressure because we're referring to atmosphere. So there is the answer on that. I think maybe I can go ahead and do some more. Short videos are good. I like short videos. It makes it look like I did a lot more work. So we'll make another video and continue on with this class shortly.